Thank you very much for the introduction and for the invitation. So in this half an hour, a bit more, I would like to discuss how first principle simulations can allow us to improve and expand the portfolio of 2D magnetic materials. And to me, this is particularly important because 2D magnetic materials have changed the way in which experimentalists approach the synthesis and the exfoliation of 2D materials. Because if you think about it, from the discovery of graphene, only few 2D materials have been explored experimentally. But the field has dramatically changed in 2016 with the first discovery of magnetism. And this has sparked a tremendous rush for new materials. Because maybe this is a semi-metal, this is a semiconductor, so maybe you're already happy with that, and they are pretty good materials, pretty easy to work with. But then when we go to magnetism, magnetism is just not one thing. So there is not just a magnetic material. There might be ferro, there may be antiferro. And in 2D, it's also important anisotropy, in plane, out of plane. And so that's why people have started to look for new and new materials to find different kinds of magnetism. And this list is not even actually comprehensive, so it should be much larger. With few exceptions, and most of these discoveries essentially rely on the experience in the 90s about layered transition metal compounds. But if you want to continue and drive this push for new and new materials, at some point we need something more than that. And so what we can do is somehow to exploit simulations. So that's what I want to discuss today. And the way to do that is maybe mimicking experiments in which new materials are found by exfoliation, but now doing with the simulation, so with the computer, which is much easier, and in an high-throughput way. So we want to rely on the fact that over the last 100 years, we have collected a lot of information about experimental crystal structures that are contained in databases like the Polling5, CSD, or COD, just to mention a few. And what we want to do is to see if among these materials we have something that can be exfoliated. Of course, this is hundreds of thousands of materials, and actually we started from roughly 400,000 materials. Doing calculations for all of them is feasible, but still challenging. So what we did was to first just look at the simple geometric criterion to select potentially interesting materials, and then started doing real calculations to see which ones can really be considered to be layered and exfoliable. So what we do is first principle simulation, particular density functional theory simulations, and the quantity that we were interested in is actually the binding energy for this structure. Of course, if you want to do 1,000 or tens of thousands of calculations, it's not possible to do it just by hand. You need somehow a way to automate all this. And so we used this platform, this Python platform. It's called AIDA, which is a way indeed to automate all the calculations and all the boring part of doing simulation, like creating input files and sending them to the cluster, waiting for the calculations to run, and then collect the results. So all of this is done by AIDA. And so we just focus on the science. And the nice thing is that then with this platform, you can even build something that can be easily shared with other people. Now, I said we want to compute binding energies, but what to do with that? So we want to find among these materials the ones that are exfoliable. So exfoliable means that the binding energy should be sufficiently small to exfoliate. And van der Waals materials should be materials where van der Waals interactions is really what is keeping the structure together. So this is what we are looking for. And the nice thing, again, about simulations is that you can do potentially things that you cannot do in experiments, like playing with parameters that you cannot access in experiments. Like you can, in DFT, you can turn on and off van der Waals interactions because typical van der Waals functionals do not account for van der Waals interactions. And so what you can do is not only to compute the binding energy of materials, but also to look at how the structure changes when you put or you don't put in the simulations van der Waals interactions. So if the material is really held together by van der Waals interactions, if you turn off van der Waals, it should just expand, especially in the direction orthogonal to the layers. And so this is what is plotted here, so the expansion interlayer distance. And for a material like graphene, you see that indeed it has a small binding energy, and it expands a lot when you turn off van der Waals interaction. So that's exactly, I mean, our target exfoliable material. So out of the calculation we did, as I said, starting from roughly 100,000 materials, so we did this calculation, and we wanted to somehow group this structure, and we decided to divide them into three groups. The one that, like graphene, indeed have a small binding energy, and the structure is really held together by van der Waals interactions that we call the easily exfoliable. And, and then we have a group of these yellow, orangish materials where the binding energy is very large. This could be still potentially interesting, but we decided to discard them. And then we have something in between that we call potentially exfoliable, because the binding energy is pretty small, so it could be possible to exfoliate them. But for sure, there is something that adds the structure together, which is not just purely van der Waals, maybe a bit of metallic bonding or something like this. And indeed, these materials can be exfoliated. So we have, for instance, one of our predictions that was then tested by Alberto. It was Gibertini that is potentially exfoliable, so it could exfoliate down to 5, 10 nanometers. But then really getting the monolayer was difficult, so that was in agreement. And so this is then the number of the number of compounds that we found. So we found essentially 2,000 of this easily exfoliable and 1,000 of the potentially one. So overall, we have 3,000 materials that, and the first ones were discussed in this paper. Actually, I'm glad to speak after all this. Since he was, yes, and he wrote also the news and views for this paper. So I was, I'm very glad to do that. And we then expanded these numbers recently by just injecting new structures into this protocol. Of course, this is not the only effort in this direction. So there are several other groups that have tried to search and find new 2D materials, either by a similar approach like ours, so let's say from the top down, from 3D compounds looking for something exfoliable, or from the bottom up, let's say, just looking at structural prototypes and just changing the possible atoms with chemically similar species. Okay, so this is just, again, maybe it's not comprehensive, but you see that this means that we have available thousands of 2D materials to play with. Of course, not all of them are magnetic, but now that we have them, we can start looking for properties, and among these, of course, we are interested into magnetism. So in our case, so for our 3,000 materials, more or less, we have started computing a bunch of properties, and for some also the magnetic ones that we want to discuss today. And again, the nice thing about using this AIDA platform is that then we can easily extract the results and put them on this materials cloud, which is a web platform where you can search for the materials in the database, look at the structure, look at the band structure, the phonon dispersion, and you can even play with the path. For the phonons, you can even look at the displacement. And if you're interested, you can check the original parent compound from which this 2D layer was extracted. And again, for those of you into simulations, you can even go and really see how the calculation was done. And if you want even to download the input file, if you want to reproduce these calculations. Now, as I was saying, we want to focus on magnetism. So given this hundreds of thousands of structures, we want to understand if it's magnetic and what is the possible magnetic order. And this is challenging because there could be many, not to mention the possibility of non-collinearity and ferrimagnetism. And so to do that in a high-throughput fashion, so we, of course, we first need to understand what's typically done in DFT calculation. So to find if the system is magnetic, what we can do is to try to break time reversal symmetry and see if this remains, if we find a stable solution. So a way to do that is to introduce what is called an occupation matrix, for instance, associated with the d orbitals. So like looking at some set of atomic orbitals on a given site. And the magnetic moment on the atom can then be expressed just as this difference. And what we can do is just to initialize the calculation for a given gas for this magnetic moment, and then let's just let the system iterate self-consistently and see if we find a stable solution. Of course, this means that we can possibly find a local minimum. So if you really want to find the ground state, we might need to test different configurations. And so to do that, we developed a workflow within AIDA and using Quantum Espresso as a simulation software, where we start indeed from a structure, and we first try to see a few guesses for possible ferromagnetic configurations, and we see if the ferromagnetic configuration is lower in energy than the non-magnetic one. If this is not the case, we take the material to be non-magnetic, and that's it. If instead we find it's potentially magnetic, so the ferromagnetic is lower, we actually even check for possible antiferromagnetic states, not going to very large supercells, but at least a 2x1 supercell at the very least. And then we perform several calculations with different starting magnetizations and see which is the lowest energy configuration. So by doing that, as I said, roughly a bit more than 1,000 monolayers, that are the ones with up to 12 atoms per unit cell, we found that more than 250 are magnetic. And that could be maybe potentially the end of the talk. But the problem is, can we be sure that our workflow is good enough to really find the ground state? Because the magnetic energy landscape is pretty complicated. And so we thought that maybe we need a more sophisticated algorithm. And recently, Louis Ponnet and others have come up with a very interesting approach. It is called ROMEO, the Robust Occupation Matrix Energy Optimizer. It doesn't just play with the starting magnetization, just with the initial magnetic moments, but really plays with the full density matrix of our manifold, like the D manifold. So really plays with a local atomic configuration. And so what it does is just to add a penalty to your density functional. And what we can do is to try to different gases for a reference configuration of the density matrix and run the system with this constraint, so that after some iterations, our density matrix will be almost equal to our reference one, and then release the constraint to find the closest local minimum of the DFT itself. And so the idea is that in this complex space of density matrices, we will have this complicated energy landscape, and we just constrain the magnetic moment, and then at some point we release the constraint, and we look for the closest local minimum. So it's a similar figure as before, but now just with the full density matrix instead of just a magnetic moment. And this is just a plot of the distance between the true density matrix and the reference one for several configurations. And so that as a function of the iteration, so you see that this distance goes to almost 0 after some steps. And then when it's small enough, we release the constraint. This difference maybe will become different from 0, but we will then find, because of course we will deviate from our reference one, but this is needed to go really to the minimum of the energy. And this way we can probe many different configurations for the density matrix. And this is really needed to find the minimum, because the energy landscape is indeed very complicated. So many minima are found. And if you just try to do a simple calculation with a starting magnetization, even starting from the right magnetization, is difficult to replicate and find the true ground state. I mean, sometimes you get the right magnetization, like in this case, the vanilla quantum espresso gets an antiferromagnet, but this is not the ground state, or you have a configuration with lower energy. In this case, instead, maybe you don't get the correct magnetic moment. So this seems to be relevant. So this algorithm seems to be pretty powerful. And so we try to redo the calculations now with ROMEO, and then we compared. And overall, actually, the comparison is pretty good. So it means that in the end, our initial workflow was not too bad. But there is a but. So again, the talk could finish here. But the problem is, can we be happy with these results based on pure DFT, or we need something more? And the problem is that for magnetic systems, typically DFT alone, it's not enough. So we need something more with localized D and F electrons, and improved results at a fairly small computational cost can be obtained by complementing DFT with terms that are inspired from the Amper model, so that to give rise to what is called DFT plus U calculations, and potentially one can even think of including additional terms like intersite instead of just on-site. And in this approach of DFT plus U calculations, there are different ways in which this U is interpreted. Sometimes it's interpreted just as a free parameter, like a stream empirical, to reproduce some experimental results, or can be computed self-consistently. And even in this case, there are different approach from the constraint RPA. And the one way we are using instead is what is called the linear response approach of Coccocioni and Gironcoli, where essentially we exploit this additional term, which is quadratic in the density, to correct an error of approximate DFT, where the energy of a system is a function of the fractional occupation of your manifold, instead of being piecewise linear as in the exact theory. In approximate DFT is typically as a spurious curvature. And so since this is quadratic, so we can use this quadratic term to kill this spurious curvature and essentially go on top of the exact result. So this means that essentially this U parameter is kind of the curvature of your DFT energy as a function of the occupation of this manifold, or if you want, you actually need to correct for a non-interacting contribution, let's say. Now, this approach has been used in manifold examples. So there is a long list of success stories for DFT plus U. Maybe not so long in the case of 2D materials. So let me just do a bit of a self-advertisement in the case of iron phosphate sulfide, where if you do just a simple DFT calculation, you get that for the experimental crystal structure, it's metallic and it is unstable. So you have unstable phonons. And you can maybe stabilize the structure at the DFT level by looking at the unstable phonons, and you get something which is non-metallic with a finite gap, but still the comparison for your frequencies is not super good. And you really need the Hubbard correction to stabilize the correct ground state and open a reasonable band gap and get a better agreement for the Raman frequencies of your phonons. Now, this comes now to explaining why we need ROMEO when we're using the U, because when we use DFT plus U, your energy landscape becomes way more complicated. So this is the calculation of several states obtained by this ROMEO approach, where you already find 14 unique states, or 14 local minima, which is already a lot at a DFT level. But now, if you take the same material and you do it at DFT plus U level, you get 189. So this means that when you do DFT plus U calculations, the energy landscape becomes a mess. And in this case, our simple Kronos workflow is not sufficient. So we really need to probe the full density matrix to get to the true ground state of the system. Now, the problem is which value of U to use, because this is an example of cobalt oxide. And as you can see, if you go from U equal to 0, where you have just a few possible states, and you increase the U, not only you see this emergence of additional local minima, but you see that the ground state changes in nature. So it goes from ferromagnet to antiferromagnet, and then again ferromagnet. And even worse, actually, at U equal to 0 is a ferromagnetic metal. At U equal to 2 is an antiferromagnetic metal. At U equal to 4, it's an antiferromagnetic insulator, and U equal to 6 is a ferromagnetic insulator. So you get all possibilities. So you need to select properly this U. And so that's why we use the linear response approach. And so we need to compute this U for all these materials, which is a fairly expensive calculations, but now it's been accelerated by implementing it in a DFPT approach, so with density functional perturbation theory. It's still expensive, but way easier than it used to be. And so we can do it for all the materials, and actually we can even run few self-consistent steps. We don't really necessarily reach convergence, but at least we have a reasonable value. And this is, for instance, the values of U that we find for different transition metals in different compounds. Now, of course, the Haber correction plays a role. So if you compare a simple DFT calculation with the DFT plus U, you get completely different results, very trivially in terms of band gap. So many metallic systems become insulator. And we can use ROMEO now to find the ground state. And so so we did calculations for 183 monolayers that are easily exfoliable, so they should be easy to obtain in experiments. And we get essentially half of them bluish, so half of them antiferromagnets, and almost half of them ferromagnets. And then within each class, we have an abundance of insulators with respect to metals. And now we can start to look for potential application of these materials, in particular looking for promising materials classes, like half metals or half semiconductors, or where you have essentially a band gap, which is smaller for one spin component than for the others, or alter magnets that are actually quite rare, as Thomas knows very well. Another thing that is potentially relevant for experiments is that, especially for the semiconducting or insulating 2D magnets, Curie temperatures are typically fairly small. And so people would like to get higher TCs. And maybe a kind of proxy for TC would be the difference in energy between the ferromagnetic and antiferromagnetic configuration. And this is just a ranking of the insulating materials that we have. So in this respect, these materials could be the most promising one, even though, of course, this difference is just a measure of the exchange parameters. And of course, it's not the whole story, especially in 2D, because we need any information about anisotropy. So if we really want now to give information to experimentalists, we need something more sophisticated. And a possible approach would be an AIDA workflow that we've been developing together with Silvia Picozzi's group, which is called Amaranta. That indeed is a workflow based on AIDA, but this time combined with VASP instead of quantum espresso to compute exchange parameters in a way slightly different from the one that all discussed before, so what is called the four-state method. That is still a way to get all the components of the spin Hamiltonian, both in the collinear case or even the non-collinear case. That is based just on DFT calculations with different configurations of the spins. But I don't want to discuss too much because I don't want to spoil Federico Orlando's poster. So if you are interested in this, you can learn more from him at the poster session later. Now, since this would be a talk about, here this workshop, this should be about spin orbit coupling. I didn't mention anything till now about spin orbit. So topology is typically a field where spin orbit coupling, of course, plays a major role. So what about churn insulators? So we haven't really tried to look at churn insulators ourselves in this 2D system. Thomas has, for instance, in a few years back. And you actually realize that there are not many. So even starting, as in this case, from thousands of materials, in the end, the number of intrinsic quantum anomalous or insulators are really just a few. But now, since we have these thousands of materials, we thought maybe we can find a way to exploit all these trivial materials to get something which is topologically non-trivial. Of course, if we want a churn insulator, we need at least one of them to be magnetic. But then, even if they are both trivial, it could be that this van der Waals heterostructure is actually topologically non-trivial. And potentially, now that you have 2 layers, there could even be a way to control the band alignment between the 2 layers that could be used as a way to change and control the topological state of our system by including or removing a band inversion between the 2 layers. And to do that, an interesting effect that we could exploit is the fact that in many materials, of course, if you have large spin-orbit coupling, the band structure will depend a lot on the orientation of magnetization. So for instance, in chromium triodide, it was shown a few years back that there is a big change in the band structure when you go from the spin out of plane or the spin in plane. We were not interested in this. That was the main target of this paper. What caught our attention was more the top of the valence band. You see that with the spins out of plane, the bands are non-degenerate, while you have the degeneracy when the spins are in plane. And in particular, you have also a change in the position of this top of the valence band. And a similar effect can be found also in other 2D magnets, like nickel iodide, just to mention one. And so this got us interested because if you combine this effect with a suitably chosen 2D material, you could have something like this, where when the magnetization is out of plane and you split the bands, you get a band inversion and potentially a topological system, while instead, when the spins are in plane, there is no band inversion and the system is trivial. So we started to look for possible candidates for these 2D materials by looking at materials in the materials cloud, so our database and the DTU database. And we were looking for materials with the top of the valence band and the gamma point, where also the top of the valence band is present for the chromium triodide and nickel iodide, but with the correct band alignment to get possibly a good topological phase. And of course, for simulation, it's important to get a commensurate lattice, but this is not really needed for experiments. So if we found a bunch of materials for both of them, and we run calculations for the possible heterostructures, and in the end, only one survived, and only one heterostructure showed the right physics. And this is the combination of nickel iodide with this quaternary compound, which is a bit thick. And in all other cases, when you really put together the 2 materials, the interface dipole essentially spoils the band alignment, which was based just on calculations for isolated monolayers. And so these are for instance, the band structure for this heterostructure for the spins out of in plane or out of plane. And the coloring is just a projection on the layers over here on the spin. So indeed, we see the right physics. And in particular, you see that spin-orbit coupling opens a bit of a gap when you have the band inversion. So to just test that this is indeed topological, we calculated the topological invariance and confirmed that indeed when there is band inversion, this gives rise to a non-trivial Chern number. And we tested that even by changing the angle of the magnetization all the way from 0 out of plane to 90, indeed you have the signature typical topological phase transition with the gap that closes and reopens. And when this happens, you have a transition from a trivial to a non-trivial state. So to summarize, I hope I can make the message that we found many 2D materials to play with, and this data is available in the Materials Cloud portal. And among these materials, we look in particular for magnetic monolayers, and we used a robust exploration strategy to find the magnetic ground state of 200 of them. And now with these materials can be used in different ways. I mean, we can find different applications, but in particular, we were much interested in creating this van der Waals heterostructure with the tunable topological properties. And so with this, I would like to thank all the people involved, the funding, and would like to thank you for your attention.